Hello and welcome back to the lecture on applied econometrics. We have been talking about heteroscedasticity. Now in today's class we are going to actually familiarize ourselves with certain tests to sort of perform to know if heteroscedasticity is present or not. So the test actually varies, and it varies depending on what assumption we take about the distribution of the error term. So we can think that the error term is actually distributed with the values of x that we have seen previously. Like as x increases, the error term, the value of the error is actually also increasing. So that we have one kind of test. Also we can like have a less restrictive kind of situation where we don't assume something like that and we do a different test. We are going to see this different test based on these different assumptions. The first test that we perform is called Goldfeld Qandt test or GQ test. Goldfeld Qandt, Q-U-A-N-D-T, Goldfeld Qandt test. So this test is somewhat restrictive. It assumes that the error term is actually distributed with the values of x. So we can basically assume the assumption is the value of ui increases with the value of xi, So if I actually plot this, so I would have a distribution something like this, distribution of the error term. So let's say this is the value of ui and this is the value of xi, and we will see something like this. If we have to perform this GQ test, so we have to have something like this. Okay, we'll see how in different situations whether we can apply GQ test, Goldfeld Qandt test or not. But this is primarily the assumption that we have to make before we actually perform the Goldfeld Qandt test. Now, if this is how the error term looks like, and if we want to understand if heteroscedasticity is present or not, so what we need to do is simply we need to see, let's say, we can divide the whole range of observations into different parts. Let's say I divide it here. Let me use a different color. Let's say I divide this here. I create one sort of wall here. I create another divider here. And what I will try to do is that I'll try to see if the variance of this part and variance of this part are significantly different. Okay, so if the variances are significantly different, say at the lower value of x and at the higher value of x, so then we can say that, well, there is heteroscedasticity. And how we do it, there is certain rules we follow. Usually we take this part as, let's say this is called, let's say the total number of observation is n, and I take some n prime from here and I take some n prime from here. So these are same the number of observations here and number of observations there, we take same, and this n prime usually is equal to 3/8 of n. So 3/8 of the total number of observation here and 3/8 of the total number of observations at the end. So these two we take. So what we are left out is this 3/8 n here, 3/8 n there. Now how we actually do the test? So we actually perform a F test here to understand if the variances are actually significantly different or not. And to do that, how we run a regression. So let's say we have for the, or in the original regression equation, we have something like beta 2x, let's say x2, and say let's say beta 3 x3 and some error term. Okay, now how we do it, we basically run the regression first for this group here and second for this group here. Okay, we run the same regression, we have the same explanatory variable, so that way we'll see the degrees of freedom that we calculate for both the regression equations are going to be same. Okay, so how we will actually see if the two the error, the variances of the error are similar or not. So what we will do is simply we will do a f test variant of f test, where we will do f is equal to, say, residual sum of square RSS2 by corresponding DOF and by RSS1 residual sum of square by corresponding DOF. Okay. So how we do for f test? We take the larger one in the numerator. Okay. So this is the part where we have larger variance. So let's call it RSS2, or you can also call it, say, RSS large. Let me use a different color, it looks a little cluttered. Let's say you also write RSS large, and the previous one, the smaller one, we call RSS 1, or we can also call it RSS small, residual sum of square small. Okay. Now how we do it is, we basically divide this corresponding residual sum of square with the degrees of freedom, and then we get the f statistic. Now what is the degrees of freedom here? So degrees of freedom here is also pretty straightforward, since we have, in both the cases, we have the number of observations same, which is n prime, and the k is basically the number of explanatory variable is also same, right? So the DOF here is, DOF in both the cases is going to be n prime minus k. All right. Now that's how we calculate the f statistic, and then we simply do a f test, and my f calculated, depending on whether it is here or here, we take a decision whether to reject or not reject the null hypothesis. So null hypothesis here is H naught is going to be that RSS1 and RSS2, or basically we can simply say the models are the model is homoscedastic, or so there is no heteroscedasticity, whereas H1 is that the model has heteroscedasticity. Model has heteroscedasticity. Heteroscedasticity. All right. So if I have my f calculated, let's say f calculated is here, so that means it is on the right side of my f critical. So if it is on the right side of my f critical, so then I basically reject the null, that the models are basically it is homoscedastic. So there is no, the variances are basically equal. So that is not the case if my f calculated is going to be on the right side of my f critical. Okay. So that's about it, and let's do a small problem, small hands-on. I'll give you this problem. Let's say I have, let's say I have this, I have a, I am running a regression with n is equal to 136, and let's say I have this model. I don't need to specify the model, I only need the degrees of freedom from here, B1, B2, x2, just the same, B3, x3 plus the error term, and then I have, let's say the residual sum of square RSS large is going to be, let's say, 1000, or RSS2, or RSS small, or RSS1 is going to be, let's say, 800. Now I have to say if this model has heteroscedasticity or not. Okay, so how do I do that? I simply get the f statistic. My f statistic calculated is going to be RSS2, and my n is, say, 136. So my n prime is going to be 3/8 of my n. So I basically took this number for my own convenience. So its r is going to be, if I multiply it, it's going to be, I think, 51. Okay, so n prime is 51. So I have 51, and my k here my degrees of freedom. So basically, to get my degrees of freedom, the number of explanatory variables, which is k, is equal to 2. So I have 51 minus 2, and here also I have 800 by 51 minus 2. We know that the degrees of freedom are basically same. So essentially what I get is I get 1.25. So that's my f calculated. Now I have to get my f critical, and my f critical is basically, what is the degrees of freedom for f critical, is f 49. Okay, so in both the cases I have same degrees of freedom, which is 49 here. Now how do I obtain this? I have to basically go get the f table. So let me actually get the f table here, f distribution table, and I usually take a significance level, alpha is equal to 0.05. So for a 0.05, so here I have, you can see that I don't have exact degrees of freedom is equal to 49, but I have the range 40 to 60. So we can get something like in between, close to 50. And here also I'll see that we don't have exact value for 49, but we have the value for 40 and 60. So basically our f statistic would lie somewhere in between these values. So this is for 40 and 60. So one could be in between these two. So 1.69 and 1.63. So let's say it is going to 1.65. And this one 1.59, 1.53, let's say it is going to be 1.55. So my f critical is going to be somewhere in between 1.655 to 1.65, right? So we can just get an approximate value, and that's enough for us because our f calculated is 1.25, which is actually smaller than my f critical. So if my f calculated is smaller than my f critical, so then that means my f calculated is actually going to lie here, So if my f calculated is going to lie here, so that means I actually reject the null hypothesis of homoscedasticity. Okay, so this is always confusing, heteroscedasticity and homoscedasticity, but yeah, basically heteroscedasticity means that the sort of disproportionate variance, and that is the basically the alternative hypothesis. So essentially we say that the models are not of equal variance, and this is how we actually conduct the this Goldfeld Qandt test. All right, so there are a few more things to talk about when we talk about Goldfeld Qandt test. So one thing is that we need to, sometimes, so we kind of said that the error term distribution is going to look like this, but there could be other situations also, right? So there could be a situation where, you can have your error term inversely distributed with x. So let's say this is looking like this, it's more like this, okay, or it could be something like this. So there could be different types of distribution of the error term, and in case suppose your variance is actually decreasing with the increasing value of x, so what we do is we simply basically change RSS1 and RSS2. We say that initially we did RSS2 by RSS1, but in these cases we will do RSS1 by RSS2. Okay, so essentially if this is your, here it is, this is your RSS1. So initially it was in the denominator, but now it will go in the numerator. So essentially you remember that when you calculate the f statistic, you need to have the higher value on the numerator here. So basically you do RSS1 by RSS2. Here also you do RSS1 by RSS2. So RSS2 goes in the denominator. All right. So this is how we do the Goldfeld Qandt test. So another type, so this is a numerical variable. We kind of got all the values of the variable, but it can also happen for qualitative variable, which is basically the dummy variable. So let's say you are trying to see the abortion rate for different religion groups, like people are actually, if religion actually influences abortion, and if the the kind of heteroscedasticity is present for that. Similarly, if you want to see the wedge for males, females, and so basically use up dummy variables. So even then you can use this GQ test, and it's a good test to do in that kind of situations. So what you have to do is you again basically get the the error, basically the residual sum squares for different dummy categories, and you kind of do the F test. So in that case you don't have to follow that 3/8 rule. So that's basically the Goldfeld Qandt test with certain restrictions. So in the next lecture we are going to see the test for heteroscedasticity where we do not have any restriction. Thank you.